So
Okay.
Okay. I think that we are good. All right. So, welcome to the University of Minnesota's at-home public talk series, Universe at Home. I'm Lindsay Gordon. I am one of the first-year grad students here in the astrophysics program, and I have with me my co-host.
Hi, I'm Emma Martin. I am an undergrad student here at the U. I'm an astrophysics major.
And so tonight we're going to give you sort of a layman's overview of the field of exoplanets and exoplanet science. So the place to begin with all of this is, what is an exoplanet? And an exoplanet is a planet that is orbiting another star. It's not planets in our solar system. It's any other star that you care to have that has a planet going around it. That planet is considered an exoplanet. And there are very formal definitions of the size of an exoplanet. For example, it can't be so big that it could collapse to become another star. And we do subclassifications of exoplanets based off of the kinds of planets that we see in our own solar system. So there are Earth-sized exoplanets, there are Jupiter-sized exoplanets, and everything in between. So one key thing that I think people get hung up on when they think about other stellar systems and planetary systems is that we live in a solar system. And because we live in a solar system, when we think of what a solar system and a planetary system looks like, we tend to think of what ours looks like. And so we think of ours as sort of like the prototype of what a planetary system looks like. But that's absolutely not the way that you should think about these things. A planetary system can have any kind of planet in any kind of order. You can have, so this one over here on the top left is what our solar system looks like. But you can have a solar system where all of the big planets that we have far out in our solar system can be right next to the star, and all of their little rocky ones can be way far out, unlike ours, which are pretty close to our star. You can have a planetary system that's all big planets. You can have a planetary system that's all small planets. It's really kind of the sky's the limit. Astronomy joke. On what you can have in terms of the makeup and the ordering of stars, of planets around other stars. So start at the very beginning, a very good place to start. The first exoplanets were discovered in 1992 by Wilsaxon and Frail. They have the incredibly boring names of PSR B1257 plus 12B and C, and the far better nicknames of Poltergeist and Phobetor. Some fields of astronomy are not good at naming things. Exoplanet people are very good at naming things. And so these are actually some very interesting planets because they don't orbit a star the way that we think of our star as a star, our sun as a star. They're actually orbiting a pulsar, which is a stellar remnant. So some star lived and then it died and it became a neutron star that's rotating super fast. It's not like a living star that's on the main sequence like our sun is. And pulsars have a very regular period of rotation, and any abnormalities in that period of rotation as it's spinning are indications that there's something else in that system causing the gravity of the system, center of gravity, to be slightly off and to cause those abnormalities in the rotation. And that's how we know that there are exoplanets there. And later on in 94, they actually discovered that there's a third exoplanet in that system, and they called it Draugr, and it is the A planet in that system. So this is actually not a real image of what this system looks like. It's concept art, but I thought it looked really cool and wanted to show you all it. So pulsar timing is just one of the many methods for exoplanet discovery. There are sort of four main methods of discovery. Two that we're going to talk about tonight are the transit method and the radial velocity method, which require lots of observations of lots of stars. And then there are two other methods that we're not really going to talk about tonight, which are pulsar timing that I just explained, as well as microlensing, which looks at how light bends around massive objects and allows us to detect exoplanets that way. So the transit method is sort of the most popular and common and prosperous method of discovering exoplanets. If you've ever been outside on a really sunny day and you held up your hand to block the light from the sun and it suddenly got dimmer from your perspective, congratulations, you've discovered the transit method of your own accord. So the transit method is looking for exoplanets based on the fact that exoplanets don't give off light. If you have a light bulb, that's the sun. If you make a plot of how bright that light bulb looks to you over time, it's just a straight line. You've got the normal brightness of the light bulb, and it's always that same brightness because we're pretty good at making light bulbs these days. But if you take your hand and assume your hand is a pretty solid object that does not radiate, I hope for your sake, and you hold it in front of that light bulb, you've blocked some of the light from that light bulb from reaching you because it's stopped by the physical object of your hand. And so that normal brightness from just the light bulb drops down to this lower brightness with your hand in the way. And that's what happens in the transit method when you're discovering exoplanets, is you have some star and it's radiating at some constant brightness, and you have an exoplanet, and the exoplanet passes in front of the star. You end up, as it comes in front of it, starting to block out some of the light, so that brightness over time is going to drop down. And then as it passes across or transits across the face of the star, you end up blocking out an amount of light proportional to the size of that exoplanet, just because it can't get through the exoplanet to get to us because it's a solid object. And so you get this sort of U or V-shaped dip in your brightness curve over time. And if you monitor lots of stars for a really long time for these signatures, you are able to pick out which stars have exoplanets blocking light from them. And then so as you do this total eclipse and then you're moving back out, you go back to being able to see the entire star. And then this exoplanet will make a lap all the way around behind the back of the star and then come back around in front, and you'll get another dip exactly the same as this one. And so what we're really looking for is that periodic nature of it. Every time it moves in front of the star, you get a dip. And if it happens consistently, then you know it's not just like a random event where, oh, there was like a meteor or an asteroid or something blocking your telescope or light from the star. You know that it's actually something in orbit. So there are some interesting things that we can learn from this. One of the drawbacks to this method is that the orientation of things relative to us is super important. If you have a light bulb and you put your hand on top of it and you are looking at a light bulb, you're still going to see all of the light from the light bulb. In the same way, if you have a star and a planet going around it from our perspective, doing like donuts around it, you're not going to see any light blocked from that exoplanet. And so you would have to use some other method. If it was massive enough, you could probably use the radial velocity method to actually be able to see any trace that that exoplanet was in that system. What's really useful is that you can get a judge of the planet's size and distance from its host star when you look at its brightness over time plot. So these are just some little doodles of them. So if you have these two stars over here on the left, you have one that is smaller and one that is larger, but they're the same distance away from the star. You can see from their plot of brightness over time that the smaller planet will cause a smaller dip and the larger planet will cause a larger dip. Then comparing horizontally, so 1 to 4 and 2 to 3, you see that these are the two small ones and they have the same small dip, but because this one is further away from its star, it has a longer orbital period, so how long it takes to do a lap around the star. And because of that, the transit period, the period between transits is much longer. It has to actually get all the way around the star along its longer lap than this one does, which is why you see less frequent dips. And the same idea for 2 and 3, where you have that same bigger dip, but you see it less frequently because it has further to go. So I am going to pass it over to Emma, who's going to tell you guys all about the radial velocity method for exoplanet discovery.
All right, cool. Hello, I'm going to be chatting about the radial velocity method. It's also called the wobble method, the Doppler method, has a lot of names. Next slide, please. So the wobble method, the radial velocity method, utilizes the fact that stars are not stationary in their little places in the universe. They orbit around a common center of mass, known as the barycenter, and you can see in this little diagram here that stars that are smaller, that have larger planets orbiting them, will create a more drastic orbit than stars that are larger that have a smaller planet orbiting them. But even still, you can notice these slight little wobbles in the star's movement. And so this shift in these wavelengths that are created by the star alert astronomers to possible orbiting bodies. So next slide, please. And this is done through the Doppler effect. So as these stars are orbiting around this common center of mass, they are emitting light, and the light is shifted. And a really common example of this is the Doppler effect. So it's the increase or decrease in the frequency of waves as the object moves towards or away from an observer. And again, a very common example would be an ambulance driving towards you. As it approaches you, the pitch of the siren gets a lot higher. And then as it drives away, as it gets further away from you, the pitch lowers. And I'm sorry, my cat is wanting attention. And so the same thing applies to light. And so as the star is moving away from us, around this little orbit that it has around the center of mass, the wavelength that it emits is slightly redshifted. And this diagram is very extreme, but it still holds. As it moves away, the light is redshifted. It's elongated, and so then as it comes towards us on the other side, the wavelengths are compressed, and it appears slightly blue. So when astronomers see this, they can say, hey, that's really interesting. There might be something causing this star to orbit around a center mass, and it might be an exoplanet. That's really interesting. Next slide. But is it better than the transit method? It's like the best. No, yes and no. I think that them working in conjunction with each other would be very effective. The radial velocity method utilizes this Doppler effect, and you observe the spectral shift, right? And if you watch that for a certain period of time, you'd be able to see how long it takes for the star to shift to redshift, back to blue shift, back to redshift. And you can say, okay, that's how long it takes for it to orbit its period of orbit. From there, using Kepler's laws, you can find the size of the orbit, and you can even determine the minimum mass of the planet. It's nice because, you can get more information out of about the system. You can get the mass of the planet, which you can't necessarily get from the transit method. It doesn't require constant supervision like the transit method, and it doesn't require space-based telescopes, which is really nice. So there's a 3.6 meter telescope dome in La Silla, Chile, which is responsible for a lot of exoplanet discoveries using this method. Next slide, please. But just like the transit method, there are limitations, and this is where using them in conjunction would be super effective. So it's great for finding bigger planets and not so much for smaller planets. Bigger exoplanets would create a more drastic wobble, quote unquote, of the star, and smaller planets just don't create that. It's still noticeable, but you have to look at it for a while. And just like the transit method, it depends on the orientation. If the star is not moving towards or away from the Earth, there's really no way to tell that there is a planet orbiting around it, except for just watching it wobble. but doesn't tell you anything about like the period of the orbit, it'd be a lot more difficult. So if you're looking at it like this blue line here, you'd be able to see the Doppler shifted light. If you're looking at it more from like a 45-degree angle, you'd see a partial Doppler shift. You'd see that something was going on, but it might be more difficult to find out like the mass of the planet. And then if you're looking at it perpendicular to the star's plane of motion, you would probably not see any Doppler shift. And even if you do detect some sort of Doppler shifted light, it might not even be an exoplanet. Low mass stars can also be detected using the Wobble method. I'm not sure how many have been detected using this method, but I know that it's just definitely possible. So I think that is all I have to say about the radial velocity method. Yes, back to Lindsay.
Thank you. So now that we know how to find exoplanets, what do we actually know about them? So this is a artist schematic of the our Milky Way that we live in. It is a drawing because we are inside of the galaxy, and it would be extremely difficult for us to take a photo of the galaxy that we are currently inside of. But this is a plot of the 3 exoplanets that we knew about back in 1993, so almost 30 years ago. And so we knew about 3 of them. We knew about the 2 from that first discovery around that pulsar, and then we had managed to squeeze out 1 more from the radial velocity method. They're so small in this plot. There's 1 right here, and the others are pretty much impossible to see on here because there's not a lot of them. Fast forward almost 30 years, and this is what the plot looks like. This is actually from earlier this year, and these numbers are now outdated. But each of these little dots is one of the over 4,000 exoplanets that we have discovered and we know about and have confirmed. The vast majority of them came from the transit method, obviously, with radial velocity at a distant second and pulsar timing, which we used to find the first 2, have only come up with 5 more since then. It really does not get used too often. And so this inset right here is a little, it's a cutout of this region right here, which is centered around us, which is where we are in our Milky Way. And we have all these neighbors, which is really sweet, I think. Updated counts as of this morning is that we have 4,575 confirmed planets in our universe with us. And then we have another almost 8,000 that are waiting on follow-up observations to be confirmed. There's a bit of a process to being a confirmed exoplanet. First you have to get the sort of sense that something is abnormal about a stellar system. Something's not quite right. You're seeing periodic dips, you're seeing some kind of wobble in the motion, and then you have to go in and actually make sure that what you're seeing is a planet and not some other effect. It could be that you have a binary system of stars that you just didn't realize. Or it could just be like an instrument effect where you have some bad data that has turned out to not be a real planet, and then you get to say you killed a planet, which is always fun. There are almost 200 confirmed multi-planet systems. I think the most famous one that people think of are the TRAPPIST system, or the TRAPPIST system, which has 7 exoplanets in it, and is relatively close to us. And so this is a plot of the known exoplanets, and they're color-coded based off of their discovery method, and you can pretty clearly see that we find most of them with the transit method. And so what this plot is for each discovered exoplanet. The x-axis is showing the orbital period of those exoplanets, and then the y-axis is showing the planet's mass relative to our Earth's mass. And so what you can see is that for the majority of these exoplanets, you're finding them with pretty short orbital periods. The Earth's orbital period is a year, so 365 days. So that would put us somewhere around here and here for 1 Earth mass. We'd be over here somewhere. So we're finding a lot of planets that have shorter periods than our Earth does. And we're also finding a lot that are significantly larger than we are, up to 1,000 times larger than we are. And so again, thinking about like, what does our solar system look like compared to other planetary systems? Not that similar. And there is an element of observational bias to these. So it is easier to find stuff that has a large effect that happens pretty frequently. So if you have a really big exoplanet that blocks a lot of light, it's much easier to find that and that dip in the brightness curve over time than it is to find something that only has like a little bit of a dip in the brightness curve over time. The same thing with the shorter orbital periods. If it happens more frequently, you're more likely to notice something because it stops being, oh, that's a weird anomaly, and starts becoming a pattern that you can track and find an exoplanet from. So it's not entirely fair to make any conclusions based about what other planetary systems look like based off of plots like these, because we are limited in our ability to find exoplanets. So now that you've heard all about exoplanets and you're like, wow, I should like go back to school and get a degree in physics and become an exoplanet scientist and study more exoplanets. Good news, you don't need to, because exoplanets is a really cool field in that they have a huge amount of citizen science opportunities. And so the main one is through Zooniverse, through the Planet Hunters TESS program. So TESS is a survey mission. It is a space telescope. And the way it works is that it takes month-long observations of different regions of the sky. So it takes its little telescope and it points at a chunk of the sky, and then it just takes images constantly for a month. And from those images, you can produce the brightness over time curves that we looked at earlier for every star in that image. And through that, you're able to, once you dig through all of them, you can find exoplanet transits or candidate exoplanet transits that need to go through the follow-up process. The problem with this is that it produces tens of thousands of light curves every month, and nobody has time to look at all of them. So they have outsourced them to the public. So Zooniverse is a website you can go on, and they release test light curves in massive batches, and they have volunteers go in and look through all of them. And if they see interesting things like these little dips, they'll go in and they will mark them, and it will help scientists come to their discoveries faster, because now me as a grad student, I don't have to sit there and page through a million different light curves. I can have like 40 people look through all of them for me. Also really cool is that if you volunteer with the mission and you find an exoplanet in the data, you get to be on the publication team for it. And you get credit as being one of the people who found another world. And it's very, very cool. And we will drop a link in the chat at the end of this if you are interested in participating in this. So by the numbers, it's really been such a success. I've had over 30,000 volunteers work on the project, looked at over 600,000 light curves, so those brightness curves over time, and they've found 90 exoplanets, well, candidate exoplanets, in just the first 2 years of this project being ongoing. So if you are interested in getting your hands on some real data and doing some exoplanet hunting, I really recommend that you check out Zooniverse. It's a really, really cool opportunity. And honestly, it's kind of fun to do. You just get to click through them, and then if you think you see something, you mark it off. So that about wraps it up for us tonight. So if you have any questions, you can drop them in the chat, and we will figure out how to answer them, hopefully. So thank you. Okay, there's nothing in the chat, so I think we are just gonna wrap it up there. Have a good night.